Welcome to Your Math Explained, where we make math simple and clear. My name is Angela. Today, we're stepping into one of the most powerful tools in trigonometry, double angle identities. These identities let us take a double angle, like 2 theta, and express all the trig functions of it using trig functions of just theta. And they appear everywhere, in calculus, in physics, in simplifying expressions, and in solving trig equations. So let's take a look at what they are. We have the 3 main ones listed on the screen here, and they are sine 2x, cos 2x, and tangent 2x. So we're going to take a quick look at how they're derived, because all of them can be derived using the sum and difference identities. So for example, sine 2x is just sine of x plus x. And then using our sum and difference identity, we get this is equal to sine x cos x plus cos x sine x. And since these two terms are identical, we can combine them into one, and this becomes 2 times sine x cos x. Now similarly, for cos 2x, that would be cos of x plus x. And then using our sum and difference identity, we get this is cos x minus sine x sine x. Simplifying this will give us cos squared x minus sine squared x. So now notice how we actually have 3 different parts to this identity. So the one that we've proven is the first one, which is cos squared x minus sine squared x. But all 3 of them are equivalent, and you can get these two by using the Pythagorean identity that sine squared x plus cos squared x is equal to 1. You just need to isolate either sine squared x or cos squared x and then substitute it in, and then you can get the other 2 identities. So the fact that we have 3 different ones to choose from means that we can pick the best one that suits our situation. And lastly, we have our tan 2x, and I'm going to leave that to you to use the sum and difference identities to prove this one here. So now let's take a look at what kind of questions we can be working with using these double angle identities. So our first question, we want to simplify 1 minus cos 2x so that it is written as only one term. So now if we scroll back up, we can see that cos 2x is the one where we can pick multiple different identities. But because we want to rewrite this so that it's only one term, we can see that the first one is not going to work, because we have cos squared x minus sine squared x. And that is not going to help us with simplifying it down to one term. Now, same thing for the third one. If we have 2 cos squared x minus 1, then what's going to happen is if we have 1 minus that, it's going to become 1 minus negative 1, which means we're going to have a 2 at the end. So in this particular situation, it is the second one that we want to choose. So that means this is going to be equal to 1 minus, and we're going to replace our cos 2x with 1 minus 2 sine squared x. And now we can see that the 1 minus 1 is going to cancel, and we're left with minus negative 2 sine squared x. So this is going to be positive 2 sine squared x. Now the other expression that we want to simplify is 1/2 of sine x times cos x. So if you look up at the identities, we can see that the one with sine x cos x is sine 2x, but we have a 2 in the front. So then what we're going to do is we're going to come back here, and then we're going to rewrite this as 2 sine x cos x. But in order to have a coefficient of 1/2, we now need to have 1/4 in front. And now the 2 sine x cos x is just equal to sine 2x. So this is 1/4 times sine 2x. For our second example, we want to solve this trig equation here. So notice how we have both cosine and sine squared. So without knowing the double angle identity, we wouldn't be able to solve this. But now that we have the double angle identities at our disposal, we can convert this cos 2 theta into 1 minus 2 sine squared theta. And the reason that we want to use this one is because we see that we already have a sine squared theta on the other side, which allows us to combine those like terms. If we had picked one of the other two, then we wouldn't get anywhere closer because we couldn't combine any like terms. So now this is equal to our right-hand side, which is 2 sine squared theta. Now we're going to move the 2 sine squared theta over to the right-hand side. So we get 1 is equal to 4 times sine squared theta. So therefore, sine theta is equal to the square root of 1 over 4. But then we would have plus or minus. So that would be plus or minus 1/2. So for the positive case, if we have sine theta is equal to positive 1/2, that tells us the reference angle, theta r, is going to be equal to pi over 6. And then for the other case, where sine theta is equal to negative 1/2, well, we would have the same reference angle, but it would just be in different quadrants. So the reference angle is also pi over 6. But for the positive case, according to our ASTC rule, we would be either in quadrant 1 or quadrant 2. So then that means we're going to get theta is equal to pi over 6 or 5 pi over 6. And then for the case where sine theta is negative, we're going to be in quadrant 3 or quadrant 4. So that means we're going to get theta is equal to 7 pi over 6 or 11 pi over 6. And since our domain here is 0 to 2 pi, that means it's only within one full rotation. So therefore, we would have these 4 solutions to this problem here. Now let's do a quick recap of what we covered in this video. We went over what the 3 major double angle identities are and how they're derived. We looked at a couple of examples on how to simplify expressions involving double angle identities. And finally, we solved a trig equation involving a double angle. And now it is your turn to give this a try. Can you simplify this expression here using what we've learned? Make sure to leave your answer in the comments below and let us know if you'd like to see more content on trig identities in the future. That's it for this video. If you found it helpful, remember to hit that like and subscribe. And if there's a topic you'd like us to cover, make sure to drop it in the comments.